So far, we've been talking about pH scale, but we haven't really actually defined a pH scale. And we have been talking about acid as things that can accept protons and bases as things that can donate protons. Now, when you've got water and the water molecules are colliding around, about 1 in 10 million times that happens, you can have one of the H's come off, one of the hydrogens come off one of the oxygen molecules and go on to the other one, on the oxygen of the other water molecule, and it makes the hydronium ion and the hydroxide ion. Of course, if they collide with each other, they go back again. It's an equilibrium process. Now, when they've made careful measurements of this, they found that the concentration of the H plus ion was 10 to the minus 7. And because every time we make an H plus ion, we actually make an OH minus ion at the same time, it has the same concentration in pure water at 25 degrees. Now, we've talked about equilibrium constants, and we give that designation for Kw, equilibrium constant for water. And we need to multiply these two concentrations. So it's 10 to the minus 7 by 10 to the minus 7. That's 10 to the minus 14. So that gives you the Kw for water at 25 degrees Celsius. It changes with the temperature, as any equilibrium constant does. Now, if we've got 0.1 molar HCl, the amount of H plus ions far exceeds the OH minus ions in the solution. Any H plus ions that are there are going to use up a bulk of the OH minus ions to make water, and it'll be mostly H plus ions. As you do a 1 in 10 dilution, you'll get less and less and less of the H plus ions until you get 10 to the minus 7, and the OH minus ions are increasing simultaneously until you get equal amounts in pure water. So the pH scale is something we've been using coincidentally, and when we did the indicators and we were testing various indicators, we made up solutions to test it, starting with 1 molar HCl and doing a 1 in 10 dilution 6 times until we got to 10 to the minus 6. 10 to the minus 7 being pure water, so we didn't have to do that dilution, we just used pure water. And if we start out with OH minus 1 molar, and we just kept diluting that, notice it's missing one here. If we just keep diluting that, we will get to the point where it's 10 to the minus 6, and that would be at pH 8, which isn't listed here. Then we would just switch over to pure water, and that's how we set up our dilution in the first place. And we made it with the serial dilution, and we wrote the pHs on the bottles and used that. So pH 7 is neutral. And it's not a mistake that it goes from 0 to 14. That relates to the Kw. So here's a nice little video. They refer to coffee as being slightly acidic. Now they also make a neutral coffee. They refer to ammonia as being a base. And the ammonia is a base. It's a weak base. And we'll be talking more about that later. So here's the video.
When water dissociates, it breaks apart into an equal number of hydrogen ions and hydroxide ions. In contrast, when other substances dissociate, they may release more hydrogen ions or more hydroxide ions. For example, hydrochloric acid releases more hydrogen ions as it dissociates, and sodium hydroxide releases more hydroxide ions. Depending on its concentration of hydrogen ions versus hydroxide ions, a substance can be classified as either an acid or a base. The pH scale measures how acidic or how basic a substance is. It ranges from 0 to 14, with 7 being neutral. When a substance has a pH of 7, like water does, it releases an equal concentration of hydrogen and hydroxide ions. When a substance has a pH of greater than 7, it's classified as a base and releases a greater concentration of hydroxide ions. The more hydroxide ions that are released, the more basic the substance is. Bases tend to feel slippery and are often used as household cleaners. Milk of magnesia and ammonia are both common bases.
Milk
If
of
a substance
magnesia
has a
is
pH of
magnesium
less than 7,
hydroxide.
it's classified as an acid and releases a greater concentration of hydrogen ions. The more hydrogen ions that are released, the more acidic the substance. Acids tend to taste sour. Lemon juice, stomach acid, and coffee are all examples of acids.
Okay, so the actual definition of the pH is minus the log of the H plus ion concentration. Because we're often dealing with numbers like 10 to the minus 7. So let's get rid of the minus for a start. And if we do it just as a log in base 10, then 10 to the minus 7 just becomes a pH of 7. So that's the pH scale for pure water. So 7 represents neutrality. And then there are a couple of calculations that you're able to do using the pH scale. But notice that each time you change the pH by 1, you actually are doing a factor of 10 in your change in H plus ion concentration. So here's a little sample calculation. We've got 4 grams of sodium hydroxide dissolved in pure water, and the amount of water is 1 litre. That's 1,000 mils. Okay, so first thing to do is 4 grams is given to you. That's a mass, so we can find the number of moles because it's the mass over the formula mass, and that turns out to be 0.10 moles of hydrogen gas. Moles of sodium hydroxide. And notice that I've actually put the extra decimal place in because it's there in the question. All right, now when we're trying to do this, the concentration of the solution is the number of moles over the volume. So it's going to be 0.1 divided by 1 litre. So it's going to be a concentration of 0.1 moles per litre. Now we use the equilibrium constant for water, and you've got 10 to the minus 14 is kW. This is 0.1, so we can substitute it. And when you put it in there, you're going to be dividing 10 to the minus 14 by 0.1. When you come to put this in your calculator, be really careful that you put in either 1 times 1 exponent 10 to the minus 14, or 1 times 10 to the minus 14, because if you don't, if you write 10 to the minus 14, then it will 10 exponent 14, it'll actually be doing 10 times it, not 1 times it. So when you put this in your calculator into your logarithmic function, and you'll end up with it coming out as pH 13. So this solution would have a pH of 13. pH of strong acids and weak bases, strong and weak acids rather. If I dissolved 0.1 moles per litre of hydrochloric acid in there, well, that's 10 to the minus 2, so we expect it to have a pH of 2, and it does. But when we have exactly the same amount by moles dissolved in water of acetic acid, we actually find that the pH is 3.4. So it's actually got less H plus ions than you would expect it to have. Because it's only a weak acid, so not all of it has dissociated.